So now the next part of 3.2 gets into specialized situations for certain distributions of data. So we're going to have the empirical rule, which is also called the 68, 95, 97, 99.7 rule for data with a bell-shaped distribution. So remember, bell-shaped is normal. So yeah, the following rule states for data having a distribution that is approximately bell-shaped, the following properties apply. So about 68% of all data fall within one standard deviation of the mean. Now remember, when they say within one standard deviation or two, that's on both sides. So one standard deviation on one side of the mean, one standard deviation on the other side of the mean combined. So technically it's kind of like two, but they use one because it's one away on either side. So just keep that in mind. The diagram helps to illustrate it as well. 95% would be for 2, 99.7 would be for 3. So you have this type of diagram, hopefully you can see it, but you got 34% on one side, again, one standard deviation on the left, one standard deviation on the right, total it together to get your 68%. Very similarly for two standard deviations, again, you got 2 on the left, 2 on the right, so 95% of the data should be in that interval. And then once you go to 3, you got pretty much all of it, 99.7%. So the types of problems we're going to be seeing is how can we relate a specific set of data and the mean and standard deviation back to this empirical rule and vice versa. So let's take a look at a couple of examples and see how this works. So let's get some starter information. So we got heights of women have bell-shaped distribution with a mean of 161 and a standard deviation of 7 centimeters. Using the empirical rule, what is the approximate percentage of women between 154 and 168 centimeters? Well, so the easiest way to do this is, well, you got to do a couple of things. The first one I would do is confirm that the mean is right smack dab in the middle. And we can do that really quick with some subtraction. So I like to just kind of put some curly braces and stuff, but this is, obviously optional. But if we look on both sides, we can see that the difference is 7 centimeters here and 7 centimeters there. So it is in the middle. That's a good thing. But now, how can we equate this 7 centimeters back to the standard deviation? Well, looking at what they said, the standard deviation is 7. So mathematically, we can quickly conclude that 7 centimeters is 1 standard deviation. Just based off of what we have here. If it says the standard deviation is 7, then 1 standard deviation is 7 centimeters. So we can automatically conclude that. But now what does the empirical rule say about 1 standard deviation? How much of the data should be in that interval from 154 to 168? 68%. Done. That's all they want. So don't overanalyze these problems. They're not really asking for, these huge calculations of any sort. They just want you to put it in the right bucket. So in this case, because it's 1 standard deviation on both sides, it's got to be 68%. Let's see what happens over here. So same thing, we got 161 in the middle, hopefully, but let's double check it. So we can see that, 161 minus 147, that's 14. And luckily we get 14 on this side. So now let's relate it back to our standard deviation. 1 standard deviation, 7 units. So how many standard deviations is 14? Yeah, it's got to be 2. So 2 standard deviations, go back to the previous page and take a look. What percentage is that? Yeah, it's 95. Done. Okay, so that's going one direction. Now let's twist it around and go the other way. So now it wants to know what heights would be needed to guarantee 99.7% of the heights lie between them. Well, So if we're just working in reversed, what does 99.7% tell us? How many standard deviations away are they looking at? Yeah, it's got to be 3. So this is 3 standard deviations. So now, if we want to get those cutoffs, we got to look at 3 standard deviations on the left side of the mean and 3 standard deviations on the right side of the mean. So let's just call them the lower and the upper. So how would we get the lower one? We know our mean is 161. We know the standard deviation is 7. So all we're doing is just doing some quick subtraction and multiplying. But be careful, make sure you multiply by 3. 3 standard deviations is what we want to do. So if we just take away 161, or excuse me, take away 21 from 161, yep, I got something in the way. So that gives us 140 centimeters. So that's on the low side. What's going to be the number on the upper side? Very similar process. We're going to add 121, which gets us up to 182. So, not terrible. Again, the math is not super complicated, but you got to understand what they're looking for. That's the key to this whole mess. So, okay, that's for a bell-shaped distribution, though. We don't always have a bell-shaped distribution, so what do we do then? Well, luckily, there was a Russian mathematician by the name of Chebyshev who thought of that. So if the distribution does not have a normal or bell-shaped distribution, then we cannot use the empirical rule. However, for any distribution, we can use Chebyshev's theorem to get some approximate percentages related to the data. So that's good. So now it says the proportion or fraction of any set of data lying within k standard deviations of the mean is always at least 1 minus 1 over k squared, where k is any positive number greater than 1. What? No, don't worry about it. We're not going to get into the fraction part of it. We're going to look at 2 specific cases of k. We want to look at when k is 2 standard deviations or 3, and that's it. So don't worry about any other types of values for k. We're only dealing with 2 and 3. When it's 2 and 3, we get these 2 percentages. So at least 3/4 or 75% of the values fall within 2, and at least 89% of the values lie within 3. Now, to be technical, this is also referred to as 88.9%, because technically they're rounding it. So if they round it to the nearest whole number, it's 89. To the nearest tenth would be 88.9. So just keep that in mind. Sometimes they refer to it in both instances, but it's still the same property. Okay, so how does this differ from what we were just doing for examples? Well, it really doesn't. It's very, very much the same. So let's see what we do. Heights of men have a bell-shaped distribution. Now, even though they say it's bell-shaped, we can still use Chebyshev's because it works for any distribution. So heights of men have a bell-shaped distribution with a mean of 173 and a standard deviation of 8. Using Chebyshev's theorem, what do we know about the percentage of men with heights that are within 2 standard deviations of the mean? Well, so what does it say? At least 3/4 or 75% of all values lie within 2 standard deviations of the mean. That's all they want you to say for that first part. Just restate the theorem. So, at least 75% of the values lie within 2 standard deviations of the mean. Done. Okay. What are the minimum and maximum heights that are within 2 standard deviations of the mean? Well, so very similar to that last example from before, we have to find those cutoffs. So we have to find that upper and lower cutoff. All right, but again, we're looking at 2 standard deviations. So the lower cutoff should be what? What do we do mathematically? We got our mean, we got our standard deviation, and we want 2 standard deviations away. So let's just put it all in. So we got 173 minus 2 times 8. So 173 minus 16, which looks like 157. So 157 centimeters on the low end, and on the upper end, oops, not subtract, but add, looks like 189. So that would be that range for 2 standard deviations. So we know at least 75% should fall in there, but it might be more. And because it's bell-shaped, we do know it's more. It's going to be up to 95%. So Chebyshev's theorem satisfied even though it says at least 75, because it's 75 or more. So, and 95 is more, so it's still valid. All right, let's try another one, and then we'll see if we can squeeze the last part in as well. Might be a little bit longer video. So, using Chebyshev's theorem and the empirical rule, what is the approximate percentage of heights that fall between 149 centimeters and 197 centimeters? Well, so now we have to figure out how far away from the middle those cutoffs are, standard deviation wise. Well, so what do we do first? We got to first see how far away from the middle they actually are. Now the middle in this case was 173. So make sure you use the right numbers. So if we subtract that, it looks like 24 maybe. And it looks like 24 on this side. So what's 24 centimeters in terms of a number of standard deviations away? Remember, 1 standard deviation was 8 units. So 24 has got to be 3. So this is 3 standard deviations away. And now we got to split it. We got Chebyshev's, and we got the empirical rule. So what does Chebyshev's say about 3 standard deviations away? How much of the data would have to fall in there? Don't forget the at least. 89% is right, but at least 89% is more right, for lack of better wording. So at least, don't forget the at least. That's important. The empirical rule, well, that's just a flat out percentage, 99.7%. All right. So that kind of gives you a sense of how you can use that standard deviation to develop these percentages. Again, it just kind of helps you expect how much data, or know what to expect for data in a specific interval away from the mean. So the last part of this is comparing 2 different populations and their variation. So how can we compare 2 different sets of data when they're talking about apples and oranges? And the answer is using the coefficient of variation, so CV for short. And it's a very quick formula. All you're doing is taking the standard deviation and dividing by the mean, and that's going to give you a decimal, and then you got to change it to a percent. So this value that you're calculating is always a percentage, so don't forget the percentage. So just to kind of see what we're talking about here, let's do these problems. So if we have heights that have an average of 68.34 inches and a standard deviation of 3.02 inches, and weights with a mean of 172.55 pounds and a standard deviation of 26.33 pounds. So the question would be like, which one's more varied, the heights or the weights? Now again, we're talking about apples and oranges. You're talking about inches and pounds. So they're definitely not the same type of data. So how can we compare their variation? And that's using the CV. So let's do the CV for the heights first. So we're going to take 3.02, divide it by 68.34, times it by 100%. And let's see what we get. 3.02 divided by 68.34 equals. So 0.0442. Okay. So I'll put it underneath it. 0.0442 times 100%. So it looks like 4.42%. All right. Well, we're not going to know if it's bad or good or what until we see the other one. So let's do the other one. So we got 26.33 divided by 172.55. Okay, let's see what that gives us. 26.33 divided by 172.55 equals 0.1526. So 15.26%. So, what's your conclusion? Which one is more varied? Higher the percentage, the more the variation. That's the long and the short of it, pretty quick. So, since the CV of weights is higher than the CV for heights, then the weights are more, more varied. So, again, you can't really get much detail about it. You know, obviously there's higher level statistics operations that you could do, but for now we're just trying to see which one's more varied. So nothing fancy. All right, so let's stop there. Long video, I know, but that wraps up 3.2. So 3.3 in the next videos. See you soon.